we'll now look at the MOS small signal model and find that it's actually very similar to the BJT small signal model. Okay, first we'll look at the triode region. And the triode region is, of course, when we have a small drain to source voltage. In this case, we're using the device actually, the device actually looks like a resistor that varies linearly with the gate to source voltage. We can define a term, GDS, which is equal to a change in the drain current with respect to the drain to source voltage. So if we take this derivative for our triode equation, we come up with an equation that looks like so. Mu times COX times W over L times VGS minus VT minus VDS. And of course, we just mentioned that the device is in the triode region when the drain to source voltage is small, so we can neglect the drain to source voltage term in most cases. Now, the resistance then becomes RDS. This is the resistance between the drain and the source, is equal to 1 over GDS. Is approximately equal to 1 divided by mu COX W over L times VGS minus VT. So we can see this is where we get a linear dependence upon the gate to source voltage for our resistance. And this is why sometimes we call the triode region the linear region. So our model for the device in the triode region is simply a voltage variable resistance. So we can change the resistance simply by changing the voltage. And one thing we'll note is that in MOS processes, we almost always use transistor devices for resistors. And this is because we can make transistors much smaller than resistors. All right, now we'll go to saturation. Much like the bipolar device in the forward active region, we have to take into account a couple of parameters. The first is how well the transistor converts voltage to current, or our transconductance GM. And this is defined as the change in drain voltage versus the change in gate to source voltage. If we go back to our equation for our saturation region and take the derivative, we would get an expression mu times COX times W over L times VGS minus VT. And remember, sometimes we substitute VOV is equal to VGS minus VT. So actually, we can write three different expressions for GM. One is GM is equal to 2 times ID divided by VOV. The other is GM is equal to mu times COX times W over L times VOV. And a third expression is GM is equal to square root of ID divided by mu times COX times W over L. Now, we don't have a base resistance in the MOS device because the gate is separated from the source, or from the channel, by a capacitor. And a capacitor ideally is a perfect insulator. So all that we have to do is actually take care of the output resistance. So we define output resistance, GDS, is equal to, or is defined as, the change in drain current with respect to the change in the drain to source voltage. And we recall that in saturation, our device only has the channel length modulation parameter that is dependent upon the drain to source voltage. And so our output resistance can be shown to be lambda times ID when the device is in saturation. Our output resistance is equal to the resistance between the drain and the source, which is equal to 1 divided by the conductance between the drain and the source. So it's equal to 1 divided by lambda times ID. So now we can draw a small signal model for our MOS device that starts at the gate. Between the gate and the source, there is a gate to source capacitance. Between the drain and the source, we have a transconductance, Gm times VGS, where our VGS voltage is the voltage across the gate to source capacitance. We have a gate to drain capacitance. And finally, we have our output resistance, RDS, or the resistance between the drain and the source. Now, this is very similar to our our bipolar junction transistor model, with the exception that R pi is infinite. C mu is kind of like CGD. C pi is kind of like CGS. Now these phenomena arise for very different reasons, but the models look very similar if you go back and look at your notes for the bipolar junction transistor model. Now, one other thing to note is that the GM for a BJT is greater than the GM for a MOS device. And the reason for this is, let's examine our expression for GM for each of these. For the BJT device, we have GM is equal to IC divided by VT, and we know that VT is approximately equal to 26 millivolts. And we know for our MOS device that one expression we had was 2 times ID divided by VOV. Now what we'll find out as we go through the course is our typical voltages for VOV are going to be in the 2 to 300 millivolt range. So the denominator is much larger for the MOS device, and this causes the MOS device to have a smaller transconductance. Another thing of note is that in a typical output resistance for each device, the BJT has a higher output resistance than a MOS device typically. And since our intrinsic gain is the product of the GM times the output resistance, typically AV for a bipolar junction transistor is greater than AV for a MOS transistor. Now, one other thing that I want to mention is we can find the total capacitance for the channel as being COX times W times L. This is our channel capacitance. Now, COX is equal to EOX, the permittivity of the oxide divided by the thickness of the oxide. And we also know that in saturation, CGS is approximately 2/3 of our C channel, and typically we say that CGD is very small, and in most approximations we'll say that CGD is approximately equal to 0 in saturation. So that's it for the small signal model for the MOS device. We'll start looking at inspection analysis in the next class.